we discussed the concept regarding the coordinates of a vector with respect to a basis. Let V be a vector space, and suppose B equals V1, V2, etc. be a basis for V. Then we know that any element of V has a unique representation. Suppose V is an element of V. Then V has the unique representation C1, V1 plus etc. plus Cn, Vn. The scalars C1, C2, etc. Cn are known as the coordinates of V relative to the basis B, and the corresponding vector C1, C2, etc. Cn, of course in Rn, is called the coordinate vector of V relative to the basis B, and is denoted by the matrix of, the vector, or it is denoted like this. We will either in square bracket or in open bracket V, and outside as a subscript we write B. Thus the coordinates of V relative to B is equal to the n tuple C1, C2, etc. Cn. Now suppose I change the order of the elements V1, V2, etc. Vn. Say I write V1, V2, or V2, V1, V3, V4, V5, V6, etc. For example, let us consider the standard basis B equals 1, 0, 0, 1 of R2. Then any x, y in R2 is expressible as x into 1, 0 plus y into 0, 1. So the coordinate vector of V relative to B is the pair x, y. Suppose I change the order of the elements in B. Say it is expressed as, say B dash is the new vector, new basis 0, 1, 1, 0. Then there is a mistake I have written. The coordinate matrix or the coordinate vector of V relative to B dash is ordered where y, x. I written this in curly bracket. It must be open bracket. So the same vector has different coordinates with respect to the same basis. It is because the ordering of elements in the basis is immaterial here. So there are some ambiguities because the same vector has different coordinate vectors relative to the same given basis as a set. So to avoid this ambiguity, we define an ordering, so that we define a sequence of basis elements. So there will be naturally an ordering. So such a basis is known as an ordered basis. So an ordered basis is a sequence of vectors which is linearly independent and spans the space. So the ordering is very important here. The first element of that ordered basis is always the first element, so that given any vector, the coordinate corresponding to the first vector will never change. So the matrix or the coordinate vector will be unique. So without any mentioning explicitly, we will assume that all the bases discussed are ordered bases. So we have certain examples. Find the coordinate vector of p of x is equal to the nth degree polynomial relative to the standard basis for Pn. Then the standard basis is 1x, x square, etc. x power n. So we assume without that this basis is ordered. Then p of x is a0 into 1 plus, which is the first element of the basis. Then a1 into x, the second element of the basis, etc. an into x raised to n. So the coordinates will appear in the order 1, a1, a0, a1, a2, etc. a power n. Therefore, the matrix of p of x, or the coordinate vector of p of x relative to s is a0, a1, etc. an. Observe that it is an element of Rn plus 1. We know that the dimension of p of n is n plus 1. Now, find the coordinate vector of v equal to 3, 4, 5, of course in R3, relative to the basis 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, sorry. Also find a u belongs to R3 such that its matrix or its coordinate vector is minus 1, 3, 2. So let us write 3, 4, 5 as C1 into the first vector 1, 0, 1 plus C2 into 1, 1, 0 plus C3 into 0, 1, 1, which gives a set of a system of three equations. C1 plus C2 equal to 3, C2 plus C3 equal to 4, C1 plus C3 equal to 5. So solving, we get C1 equal to 2, C2 equal to 1, and C3 equal to 3. Therefore, C1 is the coordinate of 1, 0, 1, which is the first vector. C2 is the coordinate of 1, 1, 0, the second vector of the basis, and C3 is the coordinate of 0, 1, 1, the third element of the ordered basis. So therefore, the coordinate vector is 2, 1, 3. And given the coordinate vector of u is minus 1, 3, 2. So minus 1, 3, 2 being the coordinate vector, it means minus 1 is the coefficient of the first basis element 1, 0, 1. 3 is the coordinate of the second basis element 1, 1, 0, and 2 of that of 0, 1, 1. Therefore, u is minus 1 into 1, 0, 1 plus 3 into 1, 1, 0 plus 2 into 0, 1, 1. So that is the vector 2, 5, 1. As a third example, we have the matrix 2 by 2 matrix A, B, C, D. So with respect to the standard basis for M22, it is the standard basis 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Then the matrix is nothing but, or the vector is A, B, C, D. As another example, find the coordinate vector of x square plus 2x minus 1 with respect to the another basis. So this is a polynomial of order 2. So we have a basis, say, if you consider this as an element of P2, then there is a basis of 3 elements, say x plus 1, x square plus x minus 1, x square minus x plus 1. Then we express x square plus 2x minus 1 as C1 into the first vector plus C2 into second vector plus C3 into third vector, which will reduce to a second order polynomial or second degree polynomial. So the comparing the coefficients of like powers of x on either side, we have a system of three equations. Solving them, we get C1 equal to half, which is the coefficient of the first vector, C2 equal to 5 by 4, the coefficient of the second vector, and C3 equal to minus 1 by 4, the coefficient of the third vector, x square minus x plus 1. Therefore, the vector relative to the given basis is half, 5 by 4, and minus 1 by 4.